Hello, my dear colleagues, and good afternoon to all. Now, it is my great privilege to get opportunity to address the well-known topic about physics, that is electromagnetic induction. Now, today we will see what is electromagnetic induction, how electromagnetic induction is happened, what is its application, what is used in our daily life. Not only that, how electromagnetic induction is related with different applications in our daily life. Where the electromagnetic induction is used, we will see slowly through our video lecture. Okay, thank you. Now let we start our path. Now the topic is electromagnetic induction. Now, before discussing the electromagnetic induction, we will discuss the two things is electricity, that is current, and magnet. Current and magnetism. Before 18th century, we will understand or scientists conclude that electricity, that is current, and magnetism are two separate entities. But scientist Oersted interlinked between them, and he gave one experiment, and that experiment is name of that experiment is Oersted experiment. Oersted experiment. What is Oersted experiment? Oersted experiment said that current carrying wire From Oersted experiment, we can conclude current carrying wire produce magnetic field. What is that? If we see the experiment, then we will clear this what is happen. Just see, there is one magnetic needle is present. That is the magnetic needle is present. And the current is, there is the one wire is present and current is passing through that. Now when the current is passing, what we will see? we see that magnetic needle is start to deflect in that direction. Or for if that is a positive current is passing from positive to negative terminal, that is positive and negative. So galvanometer, there is a magnetic needle, it start to deflect. If current is stopped, the magnet is returned to its own position. That means the magnetic needle is deflect, and the deflection is possible only when the current carrying wire acts like a magnet, and into that wire will give the one magnetic force, and that magnetic force helps to deflect the magnetic needle. So from that Oersted experiment we can conclude current carrying wire produce magnetic field. Now that means what we get from current to magnet, current to magnet. Now, is it possible? Is the reverse is possible? Magnet to current? Magnet to current? Now, the two great scientists, one Faraday, Michael Faraday, and Henry, both simultaneously give some idea. Yes, the reverse is possible, magnet to current. And that is how it is possible. They will conclude that moving magnet, they will conclude that moving magnet, Faraday's experiment, Faraday's experiment. What is it? The Faraday conclude that moving magnet will give current in closed loop. Moving magnet. Moving magnet produce current in closed loop. Now, the moving magnet produce current in closed loop, and that is electromagnetic, that is electromagnetic induction. That is electromagnetic induction. That means magnet to current. The moving magnet will give the current, and that process is called the electromagnetic induction. Now Faraday and Henry simultaneously, they will do so many experiments, one by one. We will see the experiment, and then we will conclude what is happening. Now in first experiment, experiment 1. In first experiment, there is one coil is present. There is one coil is present. Now there is so many turns is present. There is one coil is present. And one magnet is present. There is the north and south pole is present. There is north and south pole is present. Now when magnet is moving towards the coil, when magnet is moving towards the coil, then there will be, what will be happen? For a first example, the galvanometer is present here. The galvanometer will show instantaneously, galvanometer will show one deflection. Similarly, if it will away from the coil, again galvanometer will show opposite deflection. Now why galvanometer given deflection? The deflection is only possible. The charge, as soon as the magnet is moving towards the coil or away from the coil, there is charge will start to flow. And that means instantaneous current is produced. And that is shown by the galvanometer. If as soon as the magnet is in rest, there will be no deflection. Instead of, if magnet is in rest and if the coil is moving, the coil is in to and fro towards the magnet, then there also galvanometer will show the deflection. Now from that experiment, we can conclude if there is the relative motion between magnet and coil, the current will produce along the loop of the coil. And as soon as there is no relative motion, there is no deflection and production of current will be stopped. That means no charge is flowing. Now, that means that here, what is basically happening? There is, just see, there that type of figure will be happening, and there is the one thing we'll discuss later on. There is magnetic flux will passing. The magnetic flux will passing. When it will towards the coil, the magnetic flux passing through the loop will be increased. And if it will away from the coil, the magnetic flux passing through the coil will decrease. Now we will discuss what is magnetic flux. Before that, that is the experiment 1. Now experiment 2. I want to discuss the experiment 2. Now what is happening? In experiment 2, what we'll do? Just see everyone. Now instead of bar magnet, we will use solenoid. Because bar magnet has some limitation, its strength has some limitation. But if we use the solenoid, how? Just see, there is one coil is present. There is another coil that is just like one is solenoid is present. Now, there is the solenoid. Here is current is passing, and as the current is passing, it will act like a magnet. It is solenoid. There is so many turns is present. Now, if it is moving through and fro, then what will be happen? If it is moved towards the coil, then magnetic flux, the amount of magnetic flux will be increased. So deflection of the galvanometer will show. If it is away from the coil, that is the coil away from the closed loop, then the galvanometer will reflect opposite direction. Now, why we will use that solenoid? We will use solenoid to increase the strength of the magnetic field. The solenoid will itself produce generating a magnetic field, and with that it will easily we can set up the current in the another coil. That is the experiment number 2. And there is also one relative motion is required. There is also one relative motion between the two is required. But the relative motion, it is tiresome job. It is not possible to continue to do that, because this is the mechanical relative motion. That means there is one mechanical force is acting, and this mechanical force is not always constant. There has some wear and tear, and there has some limitation. So now, why will relative motion is required? The relative motion is required basically to change the magnetic field. If steady current is flowing, the steady current is flowing, but if no relative motion is not present, so there is the amount entire of flux will be constant. If flux is constant, then no magnetic field will be generated. Now experiment number 3. Now in experiment number 3, what we will do? This slide will change, nothing more. Then what we will do? Then we will use one tab key. We will use the tab key. Now, what we will do? Instead of flowing steady current, we will simply tap the key up and down, close, open. So by changing current, here what will be the instead of flowing steady current, there is current is changing. As the current is changing, so what will be? The magnetic field also will change. As the magnetic field change, there also will be magnetic flux will be changed. And magnetic flux, when the magnetic flux will be changed, there will be induced EMF will be generated. So from the 3 experiments, what we conclude? Just we want to see the one algorithm, then it is easily, so we can conclude that what is happening. Just see, everyone. Wall structure. Now we can conclude 3 experiments. From the 3 experiments, what we conclude? We conclude that first is there is changing current. When we switch on off, there is the changing current. Changing current. Now when the changing current, there is the one is related with changing current means obviously time is present. A rate of change of current. क्या देगा? What will be? Here it will give rate of change of magnetic field. A rate of change of magnetic field. Now change of magnetic field. Rate of change of magnetic field. Rate of change of magnetic field क्या देगा? Rate of change of magnetic flux. Now, the rate of change of magnetic flux, that what the magnetic flux. Now there is a one new term is present, magnetic flux. Now I will discuss what is magnetic flux. Now, the magnetic flux will give the induced EMF. And it is the ultimate give the current electricity. So that is our algorithm, and that is all about the electromagnetic induction. Now electromagnetic induction, there is one thing is very important, rate of change of current. Now rate of change of current will give the rate of change of magnetic field. Now rate of change of magnetic field will give the rate of change of magnetic flux, and rate of change of magnetic flux will give the induced EMF or current electricity. Now there is one thing is present, flux. What is magnetic flux? What is magnetic flux? Now we will discuss the magnetic flux. What is that? Now, magnetic flux. Now, in magnetic flux, it is same as electric flux. Number of field lines passing through unit area perpendicularly. Now, there is the expression. What is the expression? Basically, magnetic flux, there is a scalar for phi is equal to B dot A. Now, everyone know that all these things, B dot A, flux phi magnetic flux, phi is equal to B dot A. Now, what is B? B is the magnetic field and A is the area. Now there is the phi is equal to BA cos theta. The phi is equal to BA cos theta. Now, just see, the magnetic flux is depends on magnetic field, area of the loop, and the angle between B and A. If there is the n number of turns is present in the loop, n number of turns in the present in the loop, then magnetic flux phi, there will be n phi. For example, if n number of turns, then n BA cos theta, that will be. Therefore, for example, that is your phi, capital phi. Now phi is depends on number of turns, magnetic field produced, area of the loop, and angle between B and A. Now what magnetic flux? We understand the magnetic flux. Now what will be the magnetic field of the solenoid? The magnetic field of the solenoid, what will be? If the B and A are perpendicular, then if B and A are perpendicular, then what will it be? Then there will be cos 90. Cos 90 will be 0. So B and A both will be parallel to each other. It is the very important concept. BA and A will be parallel. So NPA, that is theta, is equal to 0 degree. Theta is equal to 0 degree. That is magnetic field and area vector both will be parallel. Then the flux will be produced, NBA. Now for solenoid, what will be? For solenoid, what we know? For solenoid, B is equal to mu 0 Ni. For B is equal to mu 0 Ni. So just see the flux, when we write down flux phi is equal to BA. So B here will be mu 0 Nia. So flux, that is the flux phi, will be produced mu 0 Nia. That is the flux will produce by the solenoid. The amount of flux will be produced by the solenoid. Now, Faraday's law. From that is the electromagnetic induction. The flux is very important. Flux, there is so many things is present, and unit dimension it is not required to speak about. Now Faraday's law. Now from that experiment, Faraday's conclude. What is conclude Faraday? Faraday's law says that induced EMF Faraday's law, induced EMF E directly proportional to minus d phi by dt. What is that? Minus d phi by dt. Why d minus? That we'll discuss later on. First, just see dE is equal to d phi by dt. That is the changing flux. That is the changing flux, magnetic flux. Now, when we put minus d dt of b mu 0 n I, phi is equal to b mu 0 n I a, flux phi a, phi for solenoid. So mu 0 n a if constant, so di by dt. So there is possible, there is one condition is possible. So by changing current, the induced EMF is generated. If current is fixed, by changing area, there is possible to induce the EMF. So there is different phenomenon is present. One by one, we will generate the induced EMF. How we will induce how the production of induced EMF happen. There is the one is present motional induced EMF. Now in motional induced EMF, what is happen, we will see later on. Next is and there is the one thing is present, that is the eddy current. Eddy current also we will discuss. Next topic we will discuss the eddy current, motional EMF, eddy current, and there is one thing is very important, that is AC generator. In this chapter, the application of is AC generator. That is the ultimate. With the help of the AC generator, the current will be produced, and that is in our daily life. If no current is present, nothing is possible. So the generation of current is the application of your electromagnetic induction. Before that, we will discuss Lenz's law. Now, what is Lenz's law? Now, what is Lenz's law? There is one negative sign is come. How the negative sign will come, we'll discuss. And first we'll discuss Lenz's law. What is Lenz's law? First we will see what is Lenz's law.
But
now, in Faraday's law, we understand E is equal to minus d phi by dt. There is one thing is present, E is equal to minus d phi by dt. Now, why the minus sign? What is the minus and why it is the negative sign is present? Whenever we discuss about the negative sign, there is one law is present, and the law is Lenz's law. The direction of induced current in circuit is such that it opposes the change which produces in the circuit. A very important law. The direction of induced current is such that it opposes the change which produces in the circuit. What is the meaning of that? What is the meaning? क्या हो रहा है इसमें? Try to understand. Just see, there is one thing is present. For example, there is the one loop. Here the loop is present. Now, here the north and south pole is present. That is the north pole is present. Now, if the north pole is, if there is no relative motion between them, then there no current will be produced. As soon as the north pole is coming towards the coil, the north pole is coming towards the coil, then what will be? There the current will be produced. Now, what will be the direction of the current? What will be the direction of the current? Now, when the magnet is coming towards the coil, there is flux is increased. Now, the coil wants to oppose the magnet. The coil wants to stay in its previous position. So coil wants to oppose. So how it is possible? That is only possible when there will be the north pole will produce. The north pole will be produced. That is the north pole. When the north pole will produce, then what will be? the direction of the current will be towards that. When it will produce in the direction that it will oppose the increasing of flux. When the flux is increased, so it will oppose. Now similarly, if the C, so that opposing is condition, that oppose condition, that will give the negative sign. Similarly, if for example, there is present, here is the North Pole and South Pole is present, now it will move away from the coil. When it will move away from the coil, what actually wants? It wants to stay in previous position. So it will want to attract. Because the flux will, when it will move that side, your flux will be decreased, but it will wants to stay in previous position. So for that reason, it will attract. So in attraction, there will be one south pole will be formed. Just see. So immediately, as soon as the direction of the current will change, and the direction of the current will be changed, that means in both the cases, so direction of the induced current is such that it opposes the change which produces in the circuit. Circuit जो प्रोड्यूस हो रहा है उसको अपोज करने के लिए डायरेक्शन ऑफ द इंड्यूस्ड करंट विल बी चेंज, एंड दैट इज द Lenz's law. Now there is one very important concept is present. Is the Lenz's law valid the conservation of energy? Yes or no? Now Lenz's law valid the conservation of energy. Now what is that? Just think about that here. That is the first case. When the North Pole moving towards the coil, there what will be happen? There North Pole will produce in front of the magnet. Now as the North Pole will produce, immediately the magnet will stop. As the magnet stop, the induced current, production of induced current will be zero. So what will be happen? So there is the conservation of energy. What is why? Now to continue the production of current, there is one applied force is required to give. Applied force. Here I will give the force. Applied force is required to give. And that applied force, that energy, that mechanical energy will be converted into electrical energy in the coil or in the circuit. So to produce or to maintain the production of current in the loop, there is one mechanical force is applied or mechanical energy is given. That energy will convert into electrical energy. Similarly, when the magnet is moving away from the coil, now what will be happening? There will be one attraction will become. Now then in attraction it will stop. As soon as it will stop, but there is required to one force is required to give opposing force before their attraction. That opposing force or energy, that mechanical energy, that is also mechanical energy, will convert into electrical energy, and that is the Lenz's law, and that will help to produce the current. And what will be the direction, we can conclude with the help of the Lenz's law.